All right, so that is we're back online. Without further ado, I'll continue with the video. I'll start with the videos, right?
Algebra-based mechanics course. Here we'll answer questions like these and more, both intuitively and rigorously by building mathematical models. At its core, physics is about observing patterns, describing them with mathematical models, and then using those models to predict the future. And that's exactly what we'll do in this course. So we will start with kinematics, where we start learning about how to describe motion, how to measure it, represent it in multiple ways, and extend those ideas into multiple dimensions. Then we'll move to dynamics, where we ask the deeper question: what causes motion to change? This will take us to forces and Newton's laws, giving us the tools to model gravity, friction, springs, and more. From there on, we'll develop some powerful ideas like energy and momentum. These will help us analyze stuff like collisions, even in complex situations like the Large Hadron Collider, without having to track every single detail. And then we'll extend these ideas to rotations, where we'll build concepts like torque and angular momentum, which will help us analyze everything from rolling objects to orbiting satellites. From there on, we'll explore oscillations and harmonic oscillators, which will help us understand springs and pendulum systems. And finally, we'll study fluids, where we'll dig deep into the idea of pressure, buoyancy, and how fluids flow. So whether you're preparing for an AP exam or taking an introductory college physics course, or just simply curious about how we as humanity unravel the rules of this physical world, well, then this course is for you. Because you won't be just watching videos. You will actively engage with the ideas through our interactive articles, where you can check your understanding thoroughly. You will also work through a wide range of practice questions. There are multiple choice questions, questions where you graph on your own, and problems.
All right, so basically, what this is saying is that there are, a lot of different. There are a couple different topics in AP Physics. Like they have the units here. But basically, it's like physics is kind of like demonstrating or like you know helping us understand different uh yeah, the words aren't coming to it, but we're basically going to be doing physics introductory, and there's going to be a lot of different topics, right? um so let's do the quote unquote learn and try. What's a physics goal? They precisely define the measurable quantities and find relationships. Okay. Okay, so basically scalars are quantities with magnitude. Oh wait, like I would I would really like if I could draw on the screen, but that's not possible. Um um give me a minute. I'm gonna make sure that the live works here. Um just bear with me for a second here. Um yeah, so let me just play live works here. Yeah, so the live works. It's no doubt with that. So yeah, so wait a second. Let me set up a whiteboard real quick. Yeah, sorry for the delay. I'll set up a whiteboard. Maybe like a Microsoft whiteboard. Yeah, sorry, it's taking a bit of time. Microsoft Whiteboard. Okay. All right. Let's just use Microsoft Whiteboard for now. Okay, I'll uh shared screen now. There we go. So we have a whiteboard. Uh, So scalars are quantities with magnitude. So just it's one directional, right? So it would be like this, right? Just it's a certain amount of mass, like 50 50 pounds, you know. Um it's there's no versus vectors are um more 2D. Like you need to specify the direction that your uh, that your vector is, I believe. So I'm just read more into these different things. So position is okay, position is this symbol, displacement is delta position, velocity is this, acceleration is this. Okay. When all vector quantities are the same dimension, their directions can be expressed. Are in the same dimension, it can be plus or minus. Okay. Drawing vectors. A vector can be represented by drawing an arrow. The length of the arrow is the magnitude. The direction it points represents the direction of the vector quantity. Okay. So the point of the vector arrow is called the tip or the head, and the other end is the tail. So the head is right here, tail is right here. A vector may be moved anywhere, may be moved anywhere in space and still represent the exact quantity as long as the direction and magnitude are not changed. So all these vectors are the same. Okay, so let's look at the example. 1D coordinate system is shown below. It can be 10 meters per second left, 10 meters per second with a left arrow, with a head pointing left, or negative 10 meters per second. Adding vectors visually. So if you want to add together two vectors, you just need to let's say you have a vector here. That's bad. And then another vector here. So if you want to add them together, just like depicted, uh, yeah, whatever. If you wanna add vectors together, let me just draw it here. Yeah, it's not working. But yeah, we just put vector 2 at they just put head to tail. And then draw a new vector. The order doesn't matter, but like it's kind of it's kind of common sense to a point. It's just like addition and subtraction. Like if you were adding a negative, if it's a negative vector, you're just adding it together. If it's something minus something, you're just gonna do, if it's a negative vector, it's a negative vector. But, oh, okay, we're not doing the angle stuff here. Oh. They help us see what the sum looks like relative to the originals, but sometimes we need to know the magnitude of the resultant vector. If this is 5m to the right and x2 is 8m to the left, how do we find the resultant? So negative 3 meters. So, I mean, this looks like it's just normal, like, addition, subtraction, because it kind of is, but it's just, I mean, yeah, west is negative and east is positive, then the sum of the vectors, so east is positive, right? So 0.3 plus, since west is negative, so I'm assuming it would be negative 0.2. Yeah, because it's negative this plus 0.3. Okay, up next video.
Let's explore the ideas of position, speed, and velocity. So let's start with an example. We have a car parked here somewhere on the road. What is its position? So let's start with that. So what is its position? Well, the meaning of position is basically location. That's it. That's what position is. But how do I measure that? Well, for that, we need a reference point. You always measure the location by measuring how far it is from some reference. So for example, let's choose this as our reference. We usually call the reference as our 0, or you can call that as an origin, whatever you want. It's not necessary, but it's convenient to do that. And now we can take we can measure this. So if we measure this, let's say it turns out to be 10 meters, we can now say, hey, the position of that car is 10 meters. But you can immediately see one problem with this. If I just said the position is 10 meters, we wouldn't know whether we're talking about 10 meters to the right or 10 meters to the left. And therefore, one way to resolve this is to say the position is 10 meters to the right. Okay, but another way to say that, to say the same thing, that the position is 10 meters to the right, another way to say this is we could choose all the markings on the right side of that origin to be positive and everything else on the left side to be negative. And so now we could say the position of that car is plus 10 meters. That automatically means it's 10 meters to the right. Now, again, it's not necessary to choose right side to be positive. You can choose left side to be positive as well. You're completely free to decide that. It's just that it's more of a convention to choose right side to be positive. And similarly, if the car was parked, say, on a vertical track, then we would usually choose upwards to be positive. Again, that's a convention, but we usually do that. And now as a result of that, look, the position of this car became minus 15 meter. The minus represents it's below our reference point. Anyways, we can go ahead and write down the position. We usually use the letter X to denote the position, but again, you can choose whatever you want. It's more of a convention to do that. So in our case, X equals 10 meters. You could write plus 10 to represent that plus on the positive side, but even if you don't write plus, it's understood. So you're not, so if you don't have any sign in front of it, it already means it's positive. But I could have also written 10 meters to the right. I could have written 10 meters, I would have drawn an arrow mark like this. All of them represent the same thing. But you can see what's important is that to represent position, you need both the magnitude, 10 meters, and the direction as a sign, or you write it or you use an arrow mark, but you have both magnitude and direction. So quantities that have both magnitude and direction are called vector quantities. So position is a vector quantity because it requires a direction, and we represent that by using an arrow mark. And what's important about the value of the position is position depends on reference frame. So it's always important to know where your reference point is, which direction you've chosen positives and negatives. Anyways, coming back, now let's make that car actually move. Let's say that car moves from here to here in 3 seconds. Now, we can define a new quantity called velocity. Velocity is a measure of how quickly the position of the car changed. And we calculate it as change in position. This triangle means delta, it means change in position, divided by the time taken for that change in position. So in our example, what is the change in position? Well, it was here to begin with. It went here. So from 10 to 25, the position has changed by 15 meters. How did I get that 15? Well, I just did 25 minus 10, right? So I did 25 meters minus 10 meters. That's the change in position. Divided by time taken, which is 3 seconds. So 25 minus 10 is 15. 15 by 3 is 5 meters per second. So what does this number mean? Well, first of all, we see a positive sign over here. That means that velocity is to the right. And that makes sense. The position has changed to the right side. Velocity is also a vector quantity, okay? Because position is a vector quantity, so velocity becomes a vector quantity. So the sign tells you which direction the position has changed. That the new position is to the right side of my initial position. And what does the number say? 5 meters per second. It says that if the car was traveling at a constant rate, it would change its position 5 meters to the right every second. So if I could see an animation of it, this is what it would look like. So in the first second, look, it changed by 5. In the next second, it changed again by 5 to the right. In the last second, again, it changed by 5 meters to the right. Now, of course, you could ask, what if the car was not moving at a constant rate? What if it was traveling a little faster earlier and then it became slower a little later? Well, then this no longer means it's traveling exactly 5 meters per second. Then this would represent an average value. But let's not worry too much about it. Okay, let's take one more example. Let's say this time our car goes from here to here in 5 seconds. Why don't you figure out what the velocity is? All right, let's see. So in the first second, look, it changed rate, it would change its position 5 meters to the right every second. So if I could see an animation of it, this is what it would look like. So in the first second, look, it changed by 5 per second. Then this would represent 5 seconds. Why don't you figure out what the velocity is? Let's not worry too much about it. Okay, let's take one more example. Let's say this time our car goes from here to here in 5 seconds.
Okay, so here to here in 5 seconds means 20 seconds. Okay. There to there in 5 seconds means 20 seconds total. 20 is delta x, and delta t is 5. So 20 over 5 is just going to be 4. Simply 4. Right? Yeah. Oh. So you want to go with.
Now, speaking about faster and slower, the new position is to the left side of the initial position. So that's what the negative sign says. What
Oh.
does 4 meters per second say? Ooh, it's now saying that
Goes
the car
from
is moving at a
here
constant
to
rate. The
here.
car would now be covering 4 meters. It's changing its position 4 meters to the left every second. It's a little slower than what
Oh, okay. That makes more sense.
we got earlier. Now, speaking about faster and slower, that brings another quantity in our mind, something that we're probably familiar with, that is speed. Well, think of speed as how quickly you travel some distance. And we calculate speed as distance over time. And again, this would be true if the car was going at a constant speed, but if it was not, this would represent the average speed, just like before. But anyways, we can now ask, well, what's the difference between speed and velocity? They sound very similar, right? Well, let's look at our examples one more time and calculate speed. Well, in the first case, what's the speed? Well, the speed over here was, or the average speed, I should say. What is the distance traveled? Well, the distance traveled is from 10 to 25, that is 15 meters. Divide by the time taken for that distance to be traveled, that is 3 seconds. And so 15 by 3 is 5. I'm getting the same answer as before, 5 meters per second. Again, what does this mean? This means that the car travels a distance of 5 meters every second, that if it was going at a constant rate, but if it was not, then this would represent the average value, just like before. So in general, we just usually call this the average speed, okay? But this is the same as before. So what's the difference between the speed and velocity? Let's look at the second example. That will clear things for us. So if we go back to our second example where the car moved back, what is the speed now? Or what is the average? What is the average speed now? Well, the average speed would be distance divided by time. Again, what is the distance traveled? This time, the distance traveled, a car came from here to here. So the distance traveled is 20. Or is it minus 20? Well, when it comes to distance, I don't care about whether it's traveling to the left or it is traveling to the right. All I care about is the distance. And the distance is 20. And that's the key difference. So over here, there will be no negative sign. So it'll be just 20 meters divided by 5 seconds. So I get 20 by 5. That is just 4 meters per second. And you can see there is no sign over here. This means the big difference between speed and velocity is speed only has a magnitude. It does not have a direction because distance does not have a direction. I don't care about which direction it is moving. And since speed does not have a direction, it is a scalar quantity. That's the big difference. You can think of speed as velocity without the direction. They both have the same units, meters per second as a standard unit, or in a more day-to-day life unit would be miles per hour. So in short, the big difference between velocity and speed is that when it comes to velocity, we care about how much the position has changed. So for example, if the car started from here, went over here, and then let's say it came back to that same position, the change in position is 0 because the car has come back to the same position, right? So as far as velocity is considered, there is no change in position. But when it comes to speed, speed says, well, I don't care about where your initial and final position is. All I care about is how much distance you traveled. And you have traveled some distance, right? Distance represents you can think of it as the odometer reading in your car. That number will keep going up, right? So you would have traveled some distance. And so the distance traveled in this round trip would not be 0. So you see, velocity is a vector quantity. Direction matters. But when it comes to speed, the direction doesn't matter.
Alright, so there we got it. The difference. Position is just where you are on there. Speed is your speed, velocity is
Speed. Well, think of speed as how quickly you travel some distance. And we calculate speed as distance over time. And again, this would be true if the car was going at a constant speed. But if it was not, this would represent.
right. Yeah, speed is what do you call it? It's the same as velocity except without the negative or positive. It's just speed is speed no matter what direction you're going. So that's the only difference. It's scalar versus velocity is a vector. So velocity you could say I'm going to the right versus I'm going to the left. It'll specify between that. But speed is just like just I'm going this fast. Doesn't matter what direction you're going for speed. For position, it's just the it matters. Oh,
Position of that car is plus 10. And
yeah. So let's go to the article. Displacement is final position minus initial position. Okay. So final position 3.5 minus 1.5, boom. There's this positioning, which is 6 minus 2, or wow, this is kind of a weird kind of thing. Oh, which object has positive displacement? Okay. This is the head, this is the tail. So positive displacement means it's displacement is this minus this. So by going in this direction, you mean you're going this to this. Meaning A is positive, C is positive. A is positive, C is positive. Yeah, A is positive, C is positive. Because the ending point minus starting point is positive. You don't swap the initial, like, it's final minus initial, right? Uh, if you're calculating progress and you got better, or you got worse, it's determined by how well did you do at the end, minus how well did you do at the beginning is the difference, how well do you do. That's a displacement kind of thing. Uh, there we go. And there's also the variables delta x is displacement. Or yeah, delta x is per displacement. Yeah. Ready to practice. Okay. Drag and rank the vector sums from most positive to most negative. Vector B minus vector A. Now, vector B is 4 meters to the left. So it's -4. -4 minus 6 is going to be -10. -10 is pretty negative. Okay, that's probably the most negative it can go. The most negative it can be. A minus. Okay, so A minus B. B is in a negative direction. All right. B is in a negative direction. So this is gonna be the most positive. This is gonna be second. This is gonna be third. So check. Got it. Okay. A toy car is being pushed across the ground. At time 0, the car's position is 3 meters to the left of the origin. At time 5, it's 2 meters to the right of the origin. At t equals 10, it's 1 meter to the left of the origin. What's the magnitude and direction of the average velocity? Okay, so at time t equals 0, the car's position is 3 meters to the left of the origin. So it's kind of, let's kind of draw it out here. It's 3 meters, 1, 2, 3 meters to the left of the origin. Time 1. At 1, 2, 3, 4, 5, or okay, 2 meters to the right. So this is time 2, 2 meters to the right. And 1 meter to the left is third point. It's third point. So what is the magnitude and direction of the average velocity between 0, right, this point here and this point here? What's the magnitude and direction? So the final minus initial. So final is -1, minus the initial, which is -3. So this is going to be 4. Or this is going to be 2, sorry, 2. 2 meters. Delta. It's that, because it's velocity, it's that over the time it took, which is 10 seconds. So it's 1/10. Or 2/10 times positive. Um. Oh, okay. I guess they didn't like the fraction. I mean, okay, they counted as correct. It just didn't. It couldn't be a fraction. I guess. Scalar or vector. This means delta. Oh shoot. Okay. Well, name. This means final x, like final position, or I think it's, well, this is velocity. We know that, right? That's obvious. This has got to be. I'm not sure. This could be displacement. This is distance is scalar, velocity is vector, displacement is vector. Okay. So this was right. So this is displacement. So it's like position of x's. So that's how you can remember it's displacement. This one is distance, it's d distance, scalar, because it's just if you go this direct, it doesn't matter the direction. If you go this or this, it's the same distance as long as they are the same length, right? And this is velocity, it's a vector because it matters what direction you're going for velocity. It's the main difference. Okay. Velocity vector VA has a magnitude of 2 meters per second and points right. VB has 6 meters per second and points left. Points left. So I assume this is right. Okay. Uh, VA equals 2 meters per second. A and C both seem to work. Dang, this is going quite slow. AP Physics might be a bit cooked, right? But at least that one, first few lesson was easy. First lesson two was easy. Alright, I'm going to take a break on the stream, right? I'm gonna oh, okay, I'll add text. So basically I'm going to be on. I'm gonna be putting stream on break for like a couple minutes until 12:15 just to get everything, just so you can take a break from all that knowledge, and you can practice it, the vectors, you can rehearse it, you can do some quizzes. Like right now you can do practice time or break, whatever you prefer. So I'm gonna mute up and take All right, we back. We back on action. So we're getting back at it. Let's do our 25-5 split. What this is, we work.
In this video, we're going to talk about something called relative velocity. This just tells us that the velocity that you measure for any object really depends upon the point of view. Let's try to understand this with an example. Let's say that you are standing over here on the ground. It's a beautiful day, you're enjoying the scenery, and suddenly you see a truck zooming past you extremely fast, something like this. And let's say you calculate its velocity and you find out that its velocity is, let's say the velocity of the truck turns out to be 100 kilometers per hour. Now, what you want to do is you get excited by this truck's motion, and so you decide to get into the car and start driving yourself. So what you do now is you get into the car. So let's put you inside the car. Here you are, all right? And suppose you start driving, let's say with the velocity of, let's say your car doesn't go quite as much as this guy, but let's say it goes at 95 kilometers per hour. Now here's the question. Now that you are inside this car, suppose you again look at this truck. What will you see the velocity of the truck to be? Do you still see it to be 100? Or do you see it to be faster or slower? Think about this. I want you to pause this video for a while and think, what would you see in
About 5 kilometers per hour.
this situation, the velocity of truck to be? Now, this could be a familiar situation for you. You may have experienced this. Let's look at things from the car's point of view. Let's see. This is what would look like once you are inside the car. All you could see is the seat of the car and the window of the car, and you could see outside that truck. The first thing I want you to note is that once you are inside this car, you don't see that car moving anymore. I mean, it might shake a little bit, but that car is not moving as seen by you. The seats, the window, if there are any passengers over there, they just stay there. And now, because of this, we can say that the speed of the car or the velocity of the car as seen from your point of view now, once you're inside the car, that velocity is 0. In other words, you are at rest. So let me write that down. You are at rest. Your car is at rest as seen by you. But instead, when you look outside, what do you see? Well, now you see the ground whizzing backwards. You use something like this. Something like that. Right? You see the ground whizzing backwards. And let's think about this. See, as seen from the ground, the car is going forward 95 kilometers every hour. So I hope this makes sense that as seen from the car, you would now see the ground going backward at 95 kilometers per hour. The ground goes backward at 95 kilometers every hour. And we can now sort of understand what's going on over here. You see the truck is traveling on the ground 100 kilometers every hour forward, but the ground itself is going backwards 95 kilometers every hour. This is like a conveyor belt that is going backwards at an extremely high speed, and some kid is trying to run on that. I hope you see that because of this, the kid will find it extremely difficult to move forward. And the same thing is going to happen for the truck. The truck keeps struggling to go forward because the ground is constantly moving back. So the question now is, if I wait for 1 hour, how much has the truck gone forward? Well, we can calculate that. So if you wait for 1 hour, you will see that the truck has gone forward by 100 kilometers on the ground. So let's write that down. Let's use this point to measure the position of the truck. So notice that the truck would have gone forward 100 kilometers in 1 hour. So this is 100 kilometers per hour. But in that 1 hour, you would also see, because the ground is going back, you would see both the truck and the ground travel back 95 kilometers. So it comes somewhere over here, travels all the way back till here maybe. So you would see that the truck and the ground, they all go together backward till here. Let's say that's 95 kilometers per hour. And now I hope you can see that in 1 hour, effectively, the truck has only gone forward. Let's see, how much is that? I'll mark it over here. How much has the truck gone forward in 1 hour? 100 minus 95, only 5 kilometers per hour. And therefore, as seen from the car, the truck only goes forward 5 kilometers every hour. So we could now say that the velocity of the truck, when you look at it from the car, is 5 kilometers per hour forward. So let's just summarize what happened. When we look from the ground, by standing on the ground over here, the truck is going forward 100 kilometers per hour. But from the car, when you look at it, it's only 5 kilometers per hour. So do you see that the velocity of the truck that you measure really depends upon where you measure it from? If you're measuring it from ground, you get one value. You measure it from the car, you get another value. That's the whole idea behind relative velocity. Velocity is a relative term. All right. And one last detail I want to tell you, a technical term that people usually use when you're talking about relative velocity is they use the word reference frame. So instead of saying that the velocity of the truck as measured by someone standing on the ground is 100 kilometers per hour, they would just say that the velocity of the truck from the ground reference frame. That's the technical term used over there. So we could say the velocity of the truck from the ground reference frame is 100 kilometers per hour. And similarly, over here, instead of saying that, the velocity of the truck from the car is, as seen from the car, is 5 kilometers per hour, they would say the velocity of the truck from the car reference frame. So we will call this as the car reference frame. I want to show you this exact situation. Take a look at this video. I shot this video from inside a car, and first of all, I don't see my car moving at all, but instead, notice the whole ground is traveling backwards very fast. And now take a look at this truck. The truck is going pretty fast with respect to ground, but notice that with respect to me, it's struggling to go forward. Its velocity, as seen by me, is extremely slow. Can you see that? I hope this convinces you that velocity is truly a relative concept.
Yeah, so as the video said, concept of relative velocity summed up. I like to sum it up at the end because it's kind of helps you learn. But relative velocity is from different reference frames. How how does the velocity change when you change reference frames? Relative to the ground versus relative on the car. The difference is if you're if you're going faster, closer to the speed of that car is gonna appear like it's slow, like it's going forward slowly, and if you overtake it, it's gonna go backwards, and or if you go at a faster speed than it's gonna feel like it's going backwards, right? So it's all dependent on where you view it, right? Hmm. Define an object as something for its internal structure is not important to the situation. When the quantities of interest are not affected by the size shape, we choose to ignore them. Okay, so the internal structure is not important to the situation. So, uh, okay, the light turns green and the car becomes speed up to the right. Visually and simply, one way to use the particle diagram. The particle is the dot that represents a car. We treat the car as an object because we just care about representing the overall motion, not the motion of anything inside the car. We shrink the car into a single point. This is a particle diagram. Okay. The particle diagram we made is a qualitative diagram and it visualizes, but it doesn't give any quantitative information. We need to add a reference frame and define the elapsed time. So what this does is it puts it in reference of delta t, meaning each interval is separated by 2 seconds, and then this is the x number of meters. So in 2 seconds, it goes from 0 to 2.5, and then 2 seconds, 2.5 to 12 to then 12 to 25 in another 2 seconds. So it's accelerating basically. Now I have quantitative information, so we have a chart, kind of like that. Motion diagrams combine particle diagrams with vector arrows to represent various motion quantities. Velocity is the change in position per unit of time, so the spacing between the dots can be used to tell. So they combine the particle diagram here with this plot here. I don't understand why though. Hmm. Yeah, the reason I'm silent is because I don't quite understand. Let's just read the answer here. It's moving in the negative direction and is speeding up. We can tell it's moving in the negative direction because the velocity is all in the negative. Oh, so this is showing what at this point in time, what's it looking like? What's the how is the velocity looking like on top of the position? So this kind of shows you like um the time and the place you're at, but this gives you additional information, which is helps you interpret it where it's it's moving in a negative velocity, and we can tell it's speeding up is from right to left. The dots get further apart and the velocity vector get longer. So the direction you go is the direction they get longer. The dots get farther apart. Okay. This one, right to left. Okay, so the first dot is the position of the earliest time. White. Is this from right to left too? But that don't make sense. This one probably is from left to right. And this one's from left to right because it's pointing in that direction, right? So this is the first one. So I can tell it's getting slower and it's going to the right and it's getting slower and slower. Positive, yeah, slower, slower. Um, yeah, and then here it's at a constant velocity. Uh, mm, that kind of helped explain everything. So, we got 12 minutes left for our work time. So
Let's learn about position time graphs and position timetables to analyze motion. Let's start by considering a car going at a constant velocity. To create a position timetable, let's take snapshots of it at, say, every 5 seconds. So here we go. Boom. And let's convert this to our familiar oil drop diagram. It's easier to work with dots. To mark positions, all we need is an axis, a vertical axis. Think of it as a number line. And we need to start somewhere, so we need to call some point as 0. So let's just call this point as 0. And then we measure all the other points. Let's say when I measure this, it turns out to be 10 meters. If this distance is 10 meters, we will now say this position is 10 meters. You can imagine we have chosen upwards to be positive, and that's why this is positive 10 meters. Then we'll measure how far this dot is from our origin. And let's say that happens to be 20 meters. In fact, that should be 20 meters because since the car is traveling with a constant velocity, it travels the same distance, right? So if this was 10 meters, this would also be 10 meters. So the total would be 20 meters. And therefore, this position now is 20 meters. Note that we are measuring always from the origin, not from here, from the origin. And same would be the case over here. This would be 30 meters, and this would be at 40 meters mark. Well, we now have our position and time recordings, so we can go ahead and fill up this position time table. Why don't you give it a shot first? All right, let's do it. So at time 0 seconds, our position was 0 meters. Then at 5 seconds, our position is 10 meters. Then at 10 seconds, 20 meters. 15 seconds, it's 30 meters. And at 20 seconds, we are at 40 meters. Ta-da, this is how we draw our position timetable. Now here's a question. If we were not shown the animation or we were not given this oil drop diagram, could we just look at the position timetable and comment on whether the car is accelerating or not? Sure. All we have to do is look at its displacements. So at 0, we have the position 0. In the first 5 seconds, it travels 10 meters. But look at what happens in the next 5 seconds. Again, it travels from 10 to 20, 10 meters. In the next 5 seconds, again, it travels 10 meters. So can you see in every 5 seconds, it keeps traveling 10 meters. That's constant velocity. So just by looking at the position time graph, you get the same information as we get from the oil drop diagram. So it's just another way of representing the same data. And guess what? There is another way to represent this data, and that is by drawing what we call a position time graph. Here, we draw the time on the horizontal axis, and we draw the position on the vertical axis. And by the way, we tend to use the symbol X to represent the position. That's just a tradition for us. Now again, before I plot it, can you try to plot the position time graph yourself first and see what kind of graph you end up with?
So I would say position versus time. So it's 0, 0, 10, 5, 20, 10. So it's kind of like a linear thing. So you can kind of make, or you can kind of put it as a function. I don't know, maybe.
All right, let's do this.
Yeah.
Feel free to use any of these because all the three are telling you
Position.
the same story. All right. So how do we calculate velocity? Well, velocity is free to use any of these because all the three are telling you the same story. All right. So how do we calculate velocity? Well, velocity is displacement over time. And for that, let's see if I can use the position timetable to do that. Well, for this, I just need to pick some time interval, and we are free to choose any time interval we want. So let's pick, say, from 10 to 15 seconds. So from 10 to 15 seconds, the time interval is 5 seconds. And in that time interval, what is the displacement? Well, you go from 20 to 30, that is 10 meters. And therefore, what is your velocity? Your velocity is 2 meters per second. And could we get the same thing from our oil drop diagram? Sure. If you go from 10 to 15, in 5 seconds, it's covering 10 meters. The exact same thing. Do we get that? Can we get that from the graph as well? Well, let's see. If we go from 10 to 15, that 5 seconds is actually this length. Because remember, in the graph, the horizontal represents the time. So this is the 5 seconds. And when we calculate displacement from 20 to 30, we are measuring this length. Because the vertical represents another object which had a graph like this, and imagine it's a straight line.
So the velocity is the
Then
slope.
again, you can say, hey, this is also an object moving at a constant velocity. Okay, here's the next one. This time I'm going to give you a table. And why don't you pause and think about what this object is doing?
So this one, the time is getting 0, 5, 10, 15, 20. So that's like normal increments of time. Position is going from 0. It's going first 5 seconds, it's barely increasing position. Then next 5 seconds, it's going a little bit faster. Next 5 seconds is going even faster. And then the next 5 seconds is going even. The position is becoming larger at a faster rate, right?
Is it going at a constant velocity?
It's kind of like kind of
In
quadratic.
the next 5 seconds, oof, look, it covers 5 meters. It's covering more and more distance.
Oh yeah, it's quadratic because the second difference, which is 3 minus 1, is the same. 5 minus 2 is the
I
same.
must be speeding up. Immediately I know
So
this object is
that's
accelerating.
quadratic.
And if we can go ahead and draw the oil drop diagram for this, it will look something like this.
Or exponential.
Well, let's look at the slope. Initially, the
Or
graph is very steep.
logarithmic,
It's very
yeah.
hard to climb this. So very high velocity.
But
Then notice as I keep climbing, it
But,
becomes easier to
yeah.
climb. It becomes less steep. Ooh, the slope decreases.
One of those.
This means the velocity becomes smaller. So that means this object must be decelerating. And looking at the table and the oil drop diagram, they too tell the same story. And I'm sure you can confirm this yourself now.
Yeah, so that's that. Alright, so after this, I think I'm gonna stop now for the stream. I've hit the limit at not the limit, but I've hit the 1 hour stream. So that's it for today. See